How much space is required to turn a single needle through every possible direction? It sounds like an elementary physical question. Yet this question leads to a counterintuitive mathematical reality. A needle can move through a space whose area, or even volume, is exactly zero, while that space still retains the full dimension of its surroundings. In 2025, mathematicians Wang and Joshua Zahl resolved this century-old conjecture in three-dimensional space, solving what is known as the three-dimensional Kakeya set problem. Their proof established a profound geometric truth. A measurement of zero volume does not equal an absence of physical structure or dimension. Wang was born in 1991 in Guilin, China. She began her academic career at Peking University before continuing her studies in France at École Polytechnique. She completed her doctorate at the Massachusetts Institute of Technology, focusing her research on the Fourier restriction problem in three-dimensional space. Wang works in harmonic analysis and geometric measure theory. She specifically examines how waves, frequencies, and geometric objects behave across multiple, overlapping scales. A recurring theme in her research is the behavior of thin, overlapping tubes. She analyzes how these tubes can point in many different directions and occupy the same region, all while remaining highly concentrated. This specific expertise in the geometric structures of concentrated, overlapping tubes provided the mathematical framework required to settle the Kakeya problem. The origins of this problem date back to 1917. Japanese mathematician Soichi Kakeya asked a deceptively simple question. What is the smallest region in a flat plane needed to fully reverse a needle of length 1? This animation shows the two most intuitive answers. If the needle rotates around one endpoint, it sweeps out a semicircle with an area of about 1.57. If it rotates around its midpoint, it sweeps out a smaller circle with an area of about 0.78. Neither is optimal. Mathematician Abram Besicovitch realized that the needle doesn't need to rotate around a single fixed point. The change of direction can be divided into extremely small angular steps, each carried out inside a long, thin triangular region. By translating and sliding these thin triangles so they heavily overlap, the total required area drops drastically. The finer this construction becomes, the greater the overlap. Because there is no positive lower bound for this area, mathematicians can construct a space, a Kakeya set, that contains a unit line segment in every direction, yet possesses a Lebesgue measure, or area, of exactly 0. Discovering a set that could occupy 0 area forced a deeper question. If the measure of space is 0, how small can the actual dimension of a Kakeya set be? This progression illustrates basic integer dimensions, a one-dimensional line, a two-dimensional plane, and a three-dimensional solid. Fractals, by contrast, possess non-integer dimensions, such as 1.26. To evaluate highly irregular sets, mathematicians use Hausdorff and Minkowski dimensions. These do not measure total area or volume. They measure geometric complexity across finer and finer scales. In 1971, Roy Davies proved that every Kakeya set located in a flat two-dimensional plane inherently has a Hausdorff dimension of 2. A geometric set can mathematically occupy 0 space in terms of measure, while retaining the absolute structural complexity, the full dimension, of the plane it inhabits. The problem becomes more difficult in 3 dimensions. Imagine a unit pencil that must point in every possible direction in space. This outlines the three-dimensional Kakeya set conjecture. It predicts that while the volume of this set may be 0, its dimension must equal a full 3. The set cannot truly collapse into a two-dimensional surface or a lower-dimensional collection of lines. It must retain structural complexity in all directions. In 1995, Thomas Wolfe proved that the dimension of a three-dimensional Kakeya set must be at least 2.5. While a major advancement, Wolfe's lower bound left a critical gap between 2.5 and the conjectured integer of 3, creating an imposing obstacle for modern geometry. Wang and Joshua Zahl approached this obstacle with a specific strategy. They replaced infinitely thin one-dimensional line segments with very thin three-dimensional tubes, creating a small mathematical neighborhood around each segment. The primary difficulty they faced was overlap. If these tubes overlap too perfectly, their combined union deceptively appears to occupy very little volume. To counter this, Wang and Zahl employed a multi-scale analysis technique. They observed how tube structures behave across coarse and fine scales, identifying formations like planar clusters and grain-like sticky bundles. Through structural estimates and volume analysis, they established a decisive geometric trade-off. If the tubes point in sufficiently different directions, they face rigid geometric restrictions. They cannot remain permanently compressed. On February 24, 2025, Wang and Zahl published their proof. They successfully demonstrated that every Kakeya set in three-dimensional Euclidean space has both Hausdorff and Minkowski dimensions equal to exactly 3. They conquered the Kakeya set conjecture in 3 dimensions, leaving the general conjecture for 4 and higher dimensions as an open frontier. On July 23, 2026, Hong Wang was awarded the Fields Medal in Philadelphia. She became the 3rd woman in the 90-year history of the award to receive the honor, and alongside Yu Deng, one of the first Chinese nationals. The International Mathematical Union recognized her extensive body of research, including her contributions to Fourier restriction, to local smoothing, and distance set problems, alongside her work on the 3-dimensional Kakeya problem. An elementary 1917 question about a rotating needle ultimately provided new perspectives on fractal geometry and the hidden structure of space itself. The geometry of a space is dictated by how its directions, locations, and overlaps are structurally organized across every scale. Wang and Zahl proved definitively that zero volume does not mean the absence of structure.